Hello, friends. This is part two of our study of gravity and potential energy, where we actually get to derive the equation for the real equation for potential energy. So when I say the real one, I mean the more accurate. So before I do that, I want to revisit the equation you learned in physics one for potential energy, which was this. If I drop an object from a height h, then the work gravity would do, right, is work equals force times distance. In this case, it's delta y, right? Uh, Delta y being h, right? And so therefore we get that the work is mgh, the force times the distance. So what we say is that's the potential energy it had at the top, that the potential energy here was mgh and the potential energy here was zero. Now, this is arbitrary. As you might have remembered, it's arbitrary where you set zero, your zero reference point, right? This is the reference. You need a reference for potential energy to equal zero. It's arbitrary. It doesn't matter where. And I'm going to go through the logic of why right now. So this is the simple derivation of MGH. It's actually a little more complex than that. I'm going to go through a little more, not really complex, but very particular. So we're going to actually define potential energy from this, right? Delta PE equals negative delta KE, but negative delta KE is negative work. So the change in potential energy is the opposite, the negative work a force would do. Would or will do, but I say would because it doesn't actually have to do it for there to be the potential energy. For work a force would do if allowed. I'm going to define it as such. That just comes from this equation. This is clearly the work energy theorem. Again, universal to everything in existence, right? Change in potential energy equals negative change in kinetic energy. Energy is conserved, as we saw. The true definition of energy is that which is conserved. So if that's the case, this must also be the case. Now, there are other forms of energy in very particular circumstances that throw, I don't say throw a wrench in this, they just throw an extra variable in this. But we're not going to touch those for a while. So for all intents and purposes of the majority of things that we're dealing with, this is universal with exceptions. Light energy, mass energy specifically are those exceptions if you guys know about those. But the majority of situations in existence, we just care about these. Because the others either aren't there or are constant. So, sorry, I don't want to clutter. I just want to simplify. Potential energy is the work a force would do, but careful, it's actually change in potential energy is that. So actually the change in potential energy here is what? It's negative mgh. We went from mgh to zero. So if potential energy final minus potential energy zero is negative mgh, you can easily say that this is zero and easily say this is mgh, and that's all good. If this is the scenario, then this is our reference. We have chosen an arbitrary reference. I easily could choose this as mgh and this is 2mgh. I could choose my zero way down here, right? And then this is 2h and this is h, right? You guys probably did that, the roller coaster question, right? Where is zero? I'm assuming you've had this dialogue somewhere in your past year or so, depending on when you took physics one. This is a very important dialogue to have in physics one that I'm assuming you've had. If you haven't, I hope that made sense. If you forgot it entirely, I hope that made sense. You need a reference, and it's arbitrary because it's the change in potential energy that's in this equation. It's the change in energy that is the work done, not the actual energy itself. So we need a reference to define the energy, and that is arbitrary. We can choose whatever we want, and that's our model, right? So arbitrary to a specific model. And if the model works, then it works. If it doesn't work, we need to choose a new reference. We need to choose a new model. Remember, these are mathematical models that work, right? And this works to say there's a zero and then, right, that works. Great. So, cool, right? So if I actually wanted to do this, what I need to do is solve for delta PE, right? And then choose that. And so what I'm doing is actually saying, okay, force times distance is change in energy. Cool. Now, what assumptions are we making here? There's really one big one. I'm hoping you said it in your head. Assumptions, really assumption. We're assuming force of gravity is constant here. That I have a constant mg acting over a distance h from like y equals h to y equals 0, y being my vertical distance value. So technically, change in potential energy, right, is what? Negative mg delta y is the true formula, if this is true. That here, my value of g, because I'm going downward, I've chosen a positive value here, which means positive is up. So in choosing these coordinates, I've chosen positive to be up, which means g in this coordinate assumption. So this is the other assumption, is coordinates, right? Then g is negative, assumption coordinates. That g is constant, 9.8 meters per second, right? Sorry, just squeezing that in there. Sorry if it's a little sloppy, but I hope the point is being made. And that delta y is actually final minus initial negative h. So I actually have negative, negative, negative. So I get delta PE equals negative m times negative 9.8 times negative h, and I get negative mgh. So I get the exact same thing here. So again, that's a little more nitty-gritty coordinate system. But the most important thing is that we're assuming FG is constant. Is it constant? No. Let's just move on to that, because that's the whole point, right? So the whole point here is that gravity is not constant. The force of gravity changes with distance, changes with position. It's attractive. It goes as the inverse square. So as the object falls, R decreases, R being toward the center of the Earth, right? Say the center of the Earth is way down here. I have a smaller radius, which means the force actually increases, which means that G actually increases. I'm going to draw these a little better. These are my arrows of logic. Follow them. They will lead you to truth. My arrows of logic. I invite you to adopt them or say your own. So this is like R decreases, therefore, or so, gravitational force increases because that's the model we're using. That's what we observe in the universe. That's what Newton theorized. Therefore, acceleration increases because acceleration and force do the same thing, because conceptually they follow the same pattern. So I didn't write that, right? But it might be nice to, because A and F are the same pattern. Because of Newton's law of gravity. Or really, I should write that as this. Because F goes as 1 over R squared, the absolute value of F, the magnitude of F, goes as 1 over R squared. because this is my because, right? Great. So once again, we're opening up the logic and getting really good. In fact, I would love for you guys to include this level of detail, not just this. This is a little too simple. Although it's correct. This is correct. And if you wrote this, I would be like, correct, but please give me the why. This is the why, right? And I'm asking you to memorize this. I'm asking you to apply these things into new circumstances because we might talk about different situations. So back to the main point. Gravity isn't constant. At least the value of it isn't. The force isn't constant. So if force is increasing, can we use mgh? Is the work done equal to mgh? No. Now it is the average force times delta y for sure. But the average force, we would have to figure out the final force and the initial force and take the average. But what if it's not evenly increasing? It's not linear at all. It's an inverse square law. The force, as we saw from here to here, that's not linear. That's a curve, which means it's weighted toward this side. So how do we figure out the average force? How do we do this? Well, there's an advanced math technique that I'm not going to teach you, but I'm going to sort of hint at. And those of you who've seen it before will know what I'm talking about. And those of you who haven't, I'm just going to give you the equation. And you're going to see that the pattern fits this, which is why I wanted to look at the pattern first. Because the pattern fits the math. And we don't need to prove the math to compare the two. So I can gift you that. And as an aside, or later in the year, if you guys want to talk about it, I can show how you get from one to the other. It's actually very simple, but it takes an advanced math. It takes a calculus technique, which Newton figured out. So let's derive this. So to properly get the potential energy formula, what we need to do is go back to this situation where an object is falling, and we could do it for just a simple object on the Earth, but I'll draw it here. And what we do is we take the force of gravity, and to get the total work done, what we're going to do is add up the force of gravity over every delta R there is here. So we have the force of gravity here, it's bigger, delta R. Force of gravity here, it's now bigger, delta R, et cetera, et cetera, et cetera, all the way to here. So we have delta R, delta R, delta R, delta R, delta R, delta R, all the way here. And here, the force ends up being really big. And so at each point, you see at each point, there's a new force, right? At each point, this one's really, really big, right? At each point, there's a new force, and it's getting steadily and steadily bigger. Remember here, the force is just a vector at every point that represents the magnitude of how many newtons is being acted on the object. So it's going to be a sum from R initial to R final, right? So we have some initial radius, and here we'll say is some final radius when it hits the surface of this object. Could go all the way to 0, but let's just stop at the surface. R0 could be at infinity or approaching infinity, it could be very far away, but I'll just say some arbitrary initial and some arbitrary final, and we clearly need to add it up that we have Fg, which is a function of R, times delta R. And what we need to do is actually make delta R really, really tiny, so we actually make delta R go to 0, which means we actually have infinite almost amount that we're adding up. And so what ends up happening is we can multiply negative gm over r squared, which is this function, at every single point times the delta r, and we're going to add all that up from r initial to r final. And what we end up getting is something amazing. Now, here's where the math comes in. You put it in the math crank, and it's magic. You know what pops out? This is so wonderful. What pops out is you end up getting that the total work done is negative GMM over R final minus negative GMM over R initial. Sorry, I got to make sure my negatives are right. Hold on, just give me a moment. Just got to make sure my negatives are right. R final is smaller. Here's what I'm doing. I'll vocalize what I'm doing. I know that work is positive. So R final is smaller, makes this bigger. So that'll make it more negative. So it's actually this. I can never remember the negatives. I just gave the formula for potential energy and I was mixing the two up. It ends up being this. Now again, math step here that I'm skipping. For those of you who know, that's called taking an integral. If you don't know what that means, let it go. This ends up being the result. And I want you guys to know this result. So specifically, what we end up getting is then, remember, the most important formula is that this is the negative work done, which of course is the negative kinetic energy change. So delta PE is negative work, which means delta PE in gravity from some initial to some final value is this. Negative GMM over R final minus negative GMM over R initial. So I've just multiplied both by negative. There's a reason why I wrote it like this. You might say, why would I include all those negative signs? Why do you hate me? And why are you making this filled with negative signs? I don't hate you. I'm not trying to confuse your brain. I'm writing it this way for a reason, although this confuses my brain too. Clearly, I just went through a moment where I had to go through that this is positive and this is negative for work, math step, and that this is negative and this is negative for change in potential energy. So this is the real formula for delta PE. Not as elegant as mg delta y, is it? But what we can do is choose a reference point. So clearly we have an inverse relationship with R, don't we? So it's, to me, logical to say as R goes to infinity, potential energy, I divide by infinity, or as the denominator approaches infinity, potential energy, I'm going to say equals zero or approaches zero. I'm going to be bold and say equals zero. So only at infinity. You know what I like doing? I like doing things that drive mathematicians crazy. Ready? I'm going to do it. Look at this. Dum, bum, 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 bum. Oh, no, you can't do that. I like doing that. Like 1 over infinity is 0. I feel so comfortable saying that because as a physicist, from that perspective, I'm like, at infinity, it is 0. And I love that solidity. And I know in my mind it's never going to get there. So technically, yes, as R approaches infinity, potential energy approaches 0. If you like that better, that is more accurate. But I like this. I don't know. It's a little more fun. I like playing in that playground. So you can join me or not. So as R approaches infinity, potential energy approaches 0. I exploded the universe. Oh no. So that's our reference. What I've done is I've added up all of the little force times distance to get the work. Force times distance, force times distance, force times distance, force times FD cosine theta the whole way. Theta is 0. So we just get F times theta, F times R, F times dr, F times delta R, F times delta R, all the way. And I get this. Notice there's no square. It's just inverse. And that comes from this math step. You can almost think of it like it's just R squared times R. 1 over R squared times R gives me that. Isn't that cool? So obviously there's the math there, and I can, as an aside, you guys can come to the math science resource room or quickly after class. Happy to teach that to you. But really, I just want you guys to know this formula. And what you're going to have in your notes is this. This is change of potential energy for gravity. That's a little clumsy, though I did put it in a box. It is correct. I think it'll behoove us to rewrite it like this. This will be the last thing of your notes. Ready? Go. The potential energy formula for gravity, full stop, is negative GMM over R. Notice how that fits with this, that if I have negative GMM over R final, that is final potential energy. And then this is minus initial potential energy. So what this does, this actually fits, doesn't it? That this is PE final, and this is PE initial. Isn't that cool? So final minus initial is change. So it works. It works. There's a consistent mathematical pattern here that works. So I can box this and say, this is the big one. This is the true formula for potential energy. It's not MGH. Now, an interesting thing, if you take MGH and you plug in the formula, and instead of H equals 0 being the surface, you have H equals 0 changed to R. So H changes to R, and R equals 0 is the center of a planet. You can then say times R, and notice what you get. G M M over R. This is imperfect. This is more of a hand wavy, but do you see that? You get the same result. It's just a way to make it make sense. The way to make it make sense. Really, you have to go through that integral, that infinite sum of step by step to get here. But notice how like this sort of hand wavy approach gets you the same place. It starts to make it make sense. Isn't that cool? So this is the formula you want to know. So the last thing you're going to want to know, and then I'll make the next video about practicing this. So we've now derived it. Now we want to practice it. So we want to say initial potential energy, careful, it's negative in the formula, plus initial kinetic energy equals final potential energy plus final kinetic energy. I would strongly encourage everybody to organize it like this. So these are the two big equations we're going to need. And clearly we need to remind ourselves that KE is 1/2 mv squared. Bring that one back. That hasn't changed. That's also not universal. But let's get to that later. We've done enough now. We've rewritten this one. It turns out this is actually an assumption as well. Oh no, I'll give you this. This is assuming we're going very slow. This is assuming we're going much, much slower than what's called light speed. So for those of you who've heard of special relativity, it changes this equation too. But let's forget that. Erase that. No, I'm good. Oh no, I need something to stay the same. Everything I'm telling you, by the way, may be rewritten someday also, because this is Newton's law of gravity. This was rewritten by Einstein. These are mathematical models that work until they don't work, and then they need a new one. So we're taking the baby steps to the boundary of human understanding. That's where I want to take you guys this year. So this is one, again, baby step or maybe big leap toward that. The more true formula for potential energy for gravity. So you're going to plug this into this equation and solve for some things next. And that is what we're doing. Let's see if I can do this better this time. I did it. Pause the video, go back. Hope that makes sense. Those are the formulas you need. Practice next. See you guys later.